on the boat and I was reading the numbers, the readouts to Silvina for several hours. So my numbers have improved. There's still a bit of an Italian twist to my numbers, but I will still give this presentation in English today. My Spanish is definitely not taking that leap forward. Okay, so the first two meetings were directly on submarine groundwater discharge. The first one, we talked about what it is, the history of the measurements, why it's important. In the second meeting, we went through the radon and radium calculations, as well as a GIS-based analysis of submarine groundwater discharge. The last two meetings take a bit of a different twist because over the years I've also worked on other types of projects and research, specifically in the coastal zone. So today we're going to talk about nature-based solutions to climate change, particularly in the coastal zone, but this can also apply to cities on rivers or other areas as well. And tomorrow we'll see how much time there is, but I'd like to move into water resources and specifically groundwater resources in small island developing states, because this is the kind of the most critical location for issues associated with climate change. And if we're lucky, if I have the time and I can figure this out, I'll also try to present some preliminary results from the work that we have been doing for the last 2 weeks on the coast here. Tomorrow, not today. I need some time tonight to work on that. But before I begin with nature-based solutions to climate change or for coastal protection associated with climate change, I'd just like to show you a quick picture I took. Where is this? Does anybody know? Close.
Yes, the story.
Yeah. And so we were measuring a well just about 20 meters from here, so upland from here. And Silvina told me I need to go down to the beach and look at the destruction from the storms. And it's funny because it's not funny, but it's not funny. But we have a location on the east coast of the United States called the Outer Banks. They're in North Carolina. And when I was driving in to the coast a week ago, my wife said, "This really reminds me of the Outer Banks here." Very similar situation. And the Outer Banks is very famous for houses that keep falling into the ocean. It's a very similar barrier island, a very long barrier island, almost 300 kilometers long, a little bit further out into the sea. So there's a big bay behind the barrier island that's almost 30 kilometers wide and more or less touches the Gulf Stream. But so the big Atlantic storms come in, the hurricanes come in and eat away at the beach. And over time, every year now, 2, 3, 4 houses fall into the ocean. So it's a very similar situation on the North Atlantic coast and now the South Atlantic coast. But while I was out there, I noticed something. I had talked last week about intertidal discharge. And if you look here, this whole area is full of intertidal discharge. And so I briefly borrowed Silvina's conductivity meter, and I went down and I put the meter in the sea, and I measured in the open water conductivity right in that surf zone was about 45 millisiemens per centimeter, so typical Atlantic Ocean conductivity. And then I dug a hole right where this intertidal discharge was coming out. And I put the conductivity meter in there, and in the seep it was about 34 millisiemens per centimeter. So relative significant mixing with the groundwater, the fresh groundwater that's in the barrier.
Sorry, John, the groundwater in the well was around 5.
Yeah, so there's so it's definitely a mix between the last incoming tide and what's coming out. And we can assume that it's about 20 to 25% fresh water then that's coming out there. And while I was there, I did a little just observation, made myself a little pathway and tried to see how much water was moving, very, very limited. And let's say we estimate that in every meter of shoreline, there was about a liter of this water coming out per minute. Probably a little less than that, but we use a liter for easy calculations. And if we assume 25% of that is fresh water, that means that for every meter of shoreline, there's 360 liters of fresh water coming out per day. Now, if you multiply that then by 100 kilometers of coast, which, you know, is a lot, but you're talking about a lot of fresh water that's just coming out of this intertidal zone every day. Now, it's not exactly the case because this was close to low tide and at high tide, as we know, you're gonna have a different process. So this is definitely an overestimate, but you can begin to do sort of simple back of the envelope calculations to try to understand how much water we're losing in this intertidal zone, how much fresh water is coming out. And as we all know, fresh water is a very precious resource down in this area, so you can begin to think about that. And I think it would be worthwhile to go down there and try to get a better sense of this, to try to better constrain this. And you can do that fairly easily by, you know, digging a trench in the beach and putting in a weir. You know what I mean by a weir? It's like a little dam. And you see. It's like 5 minutes, we're like in the past. But. Very weird. I'll take a break.
Bueno, pero no debería tener después venir a la casa para que se Sí.
Is there any way we can just mute all, this is Zoom, right? Can we mute every other audience member? I don't know if I can talk to myself that well. I'm waiting. Makes sense. It's just so many. Yeah, so I like looking at beaches, it makes me happy. especially waves. I can watch the waves all day long. That work? No, I'm young.
Ahí hablaba pero el video fue grande.
Sí.
Sí.
Sí. Me parece que es sencillo porque
Está grabando vos, amplificando, por favor. ¿Estás escuchando?
The technology is great, but sometimes.
Bien. Sí, está escuchando.
pues seguir entonces.
Okay,
Ok,
going. Okay, so I was talking about how you could potentially do this work. You could dig a bit of a channel, so it allows the seed to go into the channel, and then you, at the end of the channel, you create a weir, which is something like you could put two sticks at the end of the channel, like a little kid would do on the beach when they're growing up. And then, but you allow the water to just come over in one spot, and there you could actually measure it. You could actually just take a graduated cylinder and capture it and quantify it, and maybe do it along the beach every 100 meters, and you can get a sense, at least at low tide, of how much water is coming out. And I think that's something that is worthwhile, because one of the problems that we talked about last time here is that it's very difficult to put in the seepage meters. We showed because of the waves. Just a bit dangerous getting the seepage meters out there. And also, the radon is a bit further offshore. We can't get that close to shore with the boat because then you're in the breaker zone. And so it's nice to have some direct measurements, like they're worthwhile to do. Good master's project. It's interesting. Okay, but we're going to switch gears back now to nature-based solutions, because I think that this is an important topic that's going to grow a lot over the next several decades. I think we've realized that when we talk about coastal protection, we often, in the past, thought about hard solutions, right? So a hard solution is something like a seawall or a breakwater or a groin that goes out into the water. And we realize that these things lead to a lot of issues down the road. And therefore, we're trying to use natural solutions to protect our coastal zones. And those natural solutions can be a lot of different things. We could have things like mangroves that are planted in tropical areas that naturally reduce the energy from waves. There's a lot of research that suggests that during the Indian Ocean tsunami in 2004, the areas that were covered with mangroves on the coastline had a lot less damage associated with it than the areas where they had removed the mangroves so the people could be in their nice beachfront resorts. Those are the ones that had the most damage. So, we can do a lot of different things to reduce the vulnerability of our coastlines to climate change and to sea level rise just by using natural solutions. And I'm going to talk about this and give you two specific projects that I've worked on today. So, there's multiple things we can do in terms of nature-based solutions, or basically restore our wetlands is a big one. We want to restore wetlands. So wetlands here in this part of the world can be salt marshes. In tropical areas, we're looking at mangroves and potentially seagrass beds and things like that. Also in temperate areas, we have seagrass beds as well. And restoring wetlands is really important because wetlands reduces energy of waves. It also helps to provide ecological niches for a lot of different fish and bird species. And so we really want to restore our wetlands. We want to restore our coastlines, maybe by doing natural protection measures for our dunes. So not just putting out, once again, a rock wall or something, but actually trying to redevelop a dune system. We want to restore our forests. Obviously, for carbon sequestration isn't a really important thing, so that could be more of an inland idea. We want to change our cities to be less impermeable and more permeable. This is particularly important for the coastline, where we need that water recharge to occur. So if we have a completely impermeable surface and it rains, then obviously that's just gonna run off into the coast. And we lose that water instead of it going into the ground. So there's lots of things that we can do to restore our, let's say, coastlines or urban centers to improve our resilience for the future. And so what is resilience? Resilience is the idea of being able to recover from a natural disaster, from an event. There will always be, and there have always been, natural disasters. We had a natural disaster a few days ago here in Argentina. A really bad one, right? In Bahia Blanca, there was, I think I read 400 millimeters of rain in something like 8 hours, which is half the year's rainfall, maybe a third to half the year's rainfall in 8 hours. This system, it doesn't matter how it's built, can't really absorb that immediately, right? The question is, how do we recover? How quickly can we recover from something like that? And how can we reduce the damage associated with an event like that? Unfortunately, and this is something I'll talk about a bit tomorrow, as climate changes and the earth heats up, we'll have more extreme events. It's very likely. Let's say it's not 100% guaranteed, but it's very likely that we'll have more intense events and probably more frequent intense events. And therefore, we need to improve our resiliency. This 400 millimeters of rain mimics what's happened recently in Europe, in Greece last year. They had a very similar event. In Libya, I think 10,000 people perished in the Libya extreme event that happened a year or two ago. In the United States, where I'm from and around New York, we've had multiple 1,000-year storm events in the last decade. Right? So it's increasing. And so how do we become more resilient? And what can we do to protect our coast? So some of those things can be potentially hard measures, like putting riprap in along our coast. But honestly, once it goes over that riprap, you're not helping, and it's not improving your resilience. So what you really want to do is adapt. So maybe put your houses on stilts would be one example of adapting, or putting in some natural protection in front of your coast. For example, rebuilding a salt marsh in front of your coastline. These will improve our resiliency, and it will reduce the future vulnerability to storms. So let's talk about this a little bit more in detail. So here's some articles, a nice review article that came out a couple of years ago, Coastal Wetland Resilience through Local, Regional, and Global Conservation. What can we do? So here we have our coastal wetland, and what we can do is try to restore our coastal wetland areas. And the reasons we want to do this is because these coastal wetlands provide many different services for us, from recreation to water purification to coastal protection to ecological niches. Okay, so let's talk about some specific things we can do. One, we can build what's known as a living shoreline. Does anyone know what a living shoreline means? Know that term? So a living shoreline is the idea that we're going to essentially restore our coast to a natural system that is now, we do something, some sort of activity, some sort of implementation that then promotes the coast to grow, to rebuild plants, salt marsh plants, seagrasses, etc. That's what we're gonna have as a living shoreline. We want to have forested wetlands. So if we have areas that naturally have trees in them. So for example, parts of the Everglades are grass, other parts of them are trees, so like a bayou in Louisiana, we want to improve the ability for the forest to grow. Oyster beds are really good natural protection measures because the oysters themselves reduce the energy of an incoming storm wave as well. Oysters also filter water and clean that water. We'll get into an oyster project. But there are also some things we can do in the urban area, right? So we can increase our groom in urban spaces. We could change parking lots to grassy and allow for a bit of recharge. We can put lawns on our roofs, so we can really try to reduce that urban heat island effect. And we can also do things like vertical farming in urban areas. So we are able to improve our agricultural productivity within cities. This also helps then use the land for other things. Corals are also really important. As we know, and in tropical areas, corals can then be restored, hopefully using nursery systems to protect or to regrow corals. Sand dunes, this is more similar to our coast here, that we need to help restore our sand dunes if possible. So there's lots of things we can do. And what's interesting is to understand, how do restored sites compare to natural sites? And because one of the issues that we have is, okay, we're trying to rebuild a natural system, but it's still restored in some ways. Do restored systems succeed as well as natural systems do? For example, in trying to understand sediment deposition rates, does it encourage the growth of a salt marsh if we restore it? And I'll get into how we do this a little bit later. But preliminary evidence shows that for salt marshes and mangroves, in both cases, the restored wetlands tend to grow faster than the natural wetlands. They tend to grow faster than the natural wetlands. And this is a really good sign. Why do you think that could be? Why would a restored wetland grow faster than a natural one? Any ideas?
Because they combine structures with the line.
So in many cases, they're utilizing, let's say, knowledge of the area to help advance or increase the sediment accretion compared to a natural system. So they know, hey, this is where we're losing the sediment. Let's put our restoration here so we can then add the sediment to that spot. Whereas the natural systems, they're kind of in equilibrium, more in equilibrium with the current situation. So restored wetlands tend to grow a bit faster because we're actively enhancing the deposition rates. And I'll explain how we're going to try to do that in Venice, essentially next month in a little while. Here's another slide showing this. So this line here is the natural wetland elevation change rate. This is areas in Florida. So the natural elevation change is this line, this linear line here. And this is our restored wetlands. And you can see that in almost every case, whether it's by planting or hydrological restoration, the restored wetlands are above that natural line. So the accretion rate in the restored wetlands, the elevation change in the restored wetlands is above the natural line, the natural rate. There are a few examples where it's a bit below, but most of them are above. So it seems like restoring wetlands has a good chance or provides a good chance for the wetlands to grow faster.
So I guess that's not the point, right? Some point should have the new system comes to the.
That's the absolute goal, right? So these restored wetlands are probably starting in definitely starting in the worst situation. So the idea is that they're trying to come up to the natural situation, and then at the natural level, then they're kind of growing together. So the ultimate goal of a restored wetland is to become a natural wetland. So yeah, and
I will later go more in depth. Is there any project that seeks to actually model like the original natural say, or maybe it's not natural one, but a desirable river state in terms of sedimentation, coastal dynamics, sea currents, whatnot. And then ours to achieve that by specific model, plan of intervention.
so I'm sure that there are certain groups that are modeling this well. Like I know that there's a group in the Netherlands that's working directly on models for wetland restoration. What I can tell you is that it's a very site specific situation. So what we see, for example, on the North Sea coast of Germany is that the North Atlantic oscillation affects sedimentation rates. So when we have more stormy periods, we actually get more sedimentation because it's bringing the sand to the coast at storm. And so in the North Sea, for example, it'll be very different than here. So there's sites you have to understand very much the site specific details to get that, let's say, ideal sedimentation rate for each location. But in a perfect world, the salt marshes or mangroves are not accreting faster than sea level rise, right? Because at some point, then they're not going to be marshes or mangroves anymore, they'll just be land. And so that it's really trying to maintain that equilibrium with sea level rise. That's the goal. So I also mentioned dunes. So this is a very recent article from 2025 from a group in France that's trying to restore dunes in an area that had a relatively high level of erosion. So this could be particularly interesting for this coastline here. And what they use are what they call algo boxes, which are essentially just cordon off areas where they're actually trying to grow vegetation right in front of the dune to reduce the energy that's eating away at the base of the dune, and then hopefully allowing the dune to grow forward or advance towards the sea rather than retreat from the sea. And what they've done, they started this work in 2014, and they've monitored it for almost a decade. And what they saw in this decade is that there has been a large increase in the volume of the dune right behind the algal box position over that decade. So here we see the increase in the elevation, depending on distance from the back dune. So right behind the algal box, we've had almost a meter increase in elevation in that decade. So it seems like this algal box is a good way to protect your coastal dune system. And this is the difference between the control area and the algal box. And you can see that the plant cover inside the algal box is almost 80% after in just a year, whereas the plant cover and the control area is much lower. And it's also a seasonal thing, so the plant cover increases in the summer, decreases in the winter, increases in the summer, decreases in the winter, and grows over time. So these are potential things that you can put along your coast here to allow the dunes to grow forward. Once again, this is a really recent paper, 2025. I don't have much more information than that, but I found, I was trying to think what would be important for the coast here is dune restoration. So this might be.
That's really would be affected also by the document.
Absolutely, dune growth.
The predominant wind coming from the sea, difficult to use the wind coming from the continent,
Most dunes are grown from the sea, right? So the sand comes up off the coast and then it gets blown upland and gets caught by vegetation or a plastic bottle. And then you get the growth of the dunes. So and in many cases, you do have that wind coming from the sea, or at least it's a daily change. So you have the sea breeze, land breeze cycle, and then it just kind of builds. But we can look, or I can look more specifically into what's happening in the south coast of Italy to see if this is working, pending wind situations. But theoretically, even if the wind is blowing from the sea, it's bringing sand with it. So anyways, this algal box might be an interesting thing to look into for here because it's a very sort of low cost idea. It's really just, you have to be able to block areas off for people walking on it and then just plant it side of it. Speaking of planting, one of the important things that is happening in a lot of tropical areas is replanting mangrove systems. And replanting mangroves is a really important nature-based solution. And when you combine that with this, does anybody know what these are? They're called, probably similar name in Spanish as Italian, but it's in Italian, they use a word fascine, which is essentially just a bunch of sticks that are then, they're like natural sticks that you can find in the area, and you bundle them together. Yeah, and so here you can see that it allows the sediment to accrete on one side of them, and that's really good for mangrove restoration. And we're going to talk about these specifically in Venice in a little bit.
That wall is impermeable, no? Because you have walls on one side.
It shouldn't be completely impermeable. That's one of the things that I mean, maybe they did it here, maybe they put some sort of plastic here to allow for the water to not go through. But in many cases with fascine, you want the water to go through. So, and that's what we're gonna do. One thing that's happening right now in New York, have you heard about this? This is a really interesting thing. This is called the Billion Oyster Project. So, New York City was basically in a way built on oysters. There were so many oysters in New York Harbor in the 1700s and 1800s that it was one of the main sources of not only protein for the people that were living there, but also construction material. So they would grind down the shells and they would use the shells to build houses. Because the shells have a lot of, you can kind of glue down the powder from the shells, and it's a really nice construction material. There were so many oysters that they partially built New York based on oysters. And the thing is, they basically removed all of the oysters from New York Harbor. And a few years ago, a group decided to do this Billion Oyster Project on New York Harbor, but where they're trying to, it's a citizen science idea where they're getting school kids and people from New York to reseed New York Harbor with 1 billion oysters. So far, they've put in 200 million oysters. And the goal of this is twofold, right? One is to reduce the energy in New York Harbor. This all came out after Hurricane Sandy damaged downtown Manhattan. And the second goal is to clean the harbor itself. As you can imagine, the New York Harbor is quite polluted because of the industry there. So if you can get the oysters to remove the pollution, then you have or filter the seawater, you have a cleaner harbor. And I'm not sure about the biology, for example, in the port here in Buenos Aires, but maybe this is something that could be looked into here as well. I don't know if there are oysters here. No oysters? Okay, but you could use mussels. Mussels versus fresh water. It's too fresh. And maybe something else. There are freshwater mussels though. Okay, so you could get freshwater mussels. They have a similar impact.
Yeah, I think one problem would be that we
Would eat them. Yeah, yeah. So that's something you don't want to do. You don't want to eat.
What about the oysters in New York? They eat them.
No, they're not gonna eat these oysters, unfortunately, maybe in the future, after the harbor's been cleaned, then maybe they can take the next generation of oysters, but this current generation, they probably won't eat. But it's a nice idea, and what's great about it is it's a citizen science idea, right? So you're getting the people of New York, the school kids of New York to try to understand the natural system, the harbor of New York, and also, begin to think about all of the potential issues and resilience options associated with climate change. So once again, oyster reefs are a nice way to remove or reduce the energy associated with storm waves. So marshes are also really important, and in many cases, we want to increase the volume of our salt marshes. And this is an interesting study that I wanted to bring up, also a fairly recent study, looking at how you can actually, if you've already put in your seawall, how you can improve the resilience of your seawall by putting a marsh in front of it. So as we know by now, seawalls are not the right answer for coastal protection. Why are seawalls not the right answer for coastal protection?
because of the reflection.
And what does the reflection do? Exactly, so when you put a seawall along your coast, exactly, because there's a wave is just energy. When a wave hits the seawall, it bounces back off and it just pulls all of that sediment with it and it bounces off. So basically, when you put in a seawall, you're gonna lose your beach. More or less as simple as that. And but in certain cases, we've already done this. And in those cases, often we're now thinking, well, okay, the seawall's already here. We've got houses right behind the seawall. We can't remove the seawall and then let the houses fall into the ocean. So let's try to restore the area in front of the sea. And one of the ways we can do that potentially is by planting salt marsh or mangroves. Now, planting salt marsh is important because just putting in sediment, as we just heard, won't work because the sediment will come wash right back out. But if you plant the salt marsh, and you don't want to just put seeds in, because just seeds will get lost as well. You actually have to plant mature salt marsh grass into the area. If you plant the mature salt marsh, that will then reduce the wave energy and hopefully capture sediment. And the idea is often, is this economically justified, right? What we have to realize as environmental scientists is that there's always a compromise. It's always a cost benefit analysis. Nothing works without money. And I think this is one of the problems often in environmental science is that people want to stay there and tree, it's, you have to make a compromise. And so we have to be able to economically justify the things we're doing. And one of the ways we do this is by showing the cost savings by planting this marsh will outweigh the cost of having to rebuild the seawall of bricks, or having to add more elevation to the seawall when the sea level rises. So this is one of the important things that we have to think about. Is it economically viable? And I'll talk about that with our Venice project a little bit later. So this is the same paper, and they show that when they put salt marsh in front of the seawalls, that they get a very large reduction in wave energy in front of the seawall. So even just a short salt marsh area of 20 meters, if you use Phragmites, which is a very common salt marsh grass, you can get a 60% reduction in wave energy with just 20 meters of salt marsh in front of your seawall. The other types of salt marsh grasses are a little bit less, but still effective. And really, most of that help is within the first 20 to 30 meters. So you don't have to have a 100-meter long salt marsh in front of your seawall. You can do it within a few meters. So salt marshes are really good for reducing wave energy. Typical situation with seawalls, I should have shown this earlier, but this is exactly what we talked about. You have a beach, you put a seawall in front of the community, and then eventually you lose your beach. So what do we want to do now is we want to put either salt marshes or mangroves in front of our seawall. This is an idea from Fiji, from the island of Fiji, or one of the islands of Fiji. Where they would also put boulders. Yeah, this is a hard protection, but the seawall's already there. So we could put some boulders in front of the beach. But the boulders are a little bit better than the seawall because they allow the water to kind of go through this area. And then behind it, they have now a row of specific types of vegetation, which help to stabilize some sediment. And then we have the seawall, and then we have our protected community behind it. So once again, a bit of a nature-based solution, in this case a twofold, so the mangroves and then these plants here, the vetiver plants in front of our seawall. Okay, so that brings me to a couple of our actual projects. So first project I want to talk about is a living shoreline project that we put together on the coast of Connecticut in Long Island Sound. Now, this is not something you would do necessarily in front of your beaches, but maybe in a bit of a harbor area or a bay area where you're not really using the beach for recreation. And what we do is we put in what's called reef falls. And this is a picture of a storm that hit the area, and you can see the waves breaking on this, what we're going to call living shoreline in a minute. But before I get into what this living shoreline is and how we do it, I would like to tell you just briefly why we did it here. This area here was a beautiful marsh for many centuries at the base of a large river that comes out into the Long Island Sound. But the problem is, it was a beautiful marsh and it attracted a lot of ducks. And the problem with attracting a lot of ducks in America is that you get a lot of duck hunters. And if you have a lot of duck hunters, especially in the 1900s, they would shoot ducks with lead pellets. And so over the years, hundreds of tons of lead got into the salt marsh. Lead, as we know, is very dangerous for biological communities and ecosystems. So about 20 years ago, they went in there and they dug the marsh up. They dug it all up, the whole marsh. They just tore it apart and then sieved it and removed the lead bullets and then just dumped it back there, but then destroyed the marsh. And then after they dumped it back there, the next storm came through. I think it was basically at the this point, Hurricane Sandy came through and just removed all of that. So we were left with a naked area. And so we use this as a study site to see if something called reef balls would work. And the idea behind the reef ball is that it encourages biological growth on the reef ball. So things like mussels and oysters will attach to it. And then that will essentially break some waves and then allow for salt marsh to grow behind it. It's a wave action area. So the goal for this was not to build a breakwater. We did not want to build a breakwater. We should not be building breakwaters anymore. And somebody should tell, where was this? Mar del Tuyú as well, or somewhere else? So
Las Zonas,
Las Zonas,
norte.
yeah. So they should not build breakwaters anymore, but they're building breakwaters. I was very shocked to see this. We were riding along the coast.
John, this is a brand new project.
It's a brand new project. So this is not a breakwater from 30 years ago.
Now it's 2 years, and I'm still building more.
It's a 2-year-old breakwater. And the problem, building breakwaters is not a nature-based solution. This is a hard solution. And what's going to happen is you're going to have erosion elsewhere. So these people might be, and that guy looks like he's pretty rich. So he's going to be happy. His little beach is still there, but those people down there are going to lose the beach. And then it becomes a terrible process because then they have to build a breakwater. And then the people next to them are going to lose the beach. And then they have to build a breakwater. And eventually you just have this armored coastline. We don't want that. It's not pretty. And eventually somebody's going to lose. And this got so intense in the United States that people were like fighting each other, neighbors, over building illegal groins and breakwaters. And once again, too many guns in the US, it gets a bit intense in certain cases. So we don't want to build breakwaters. That was not our goal. We don't want to build a breakwater. What we want, even though it looks a little bit like a breakwater, what we want to do is we want to build a living shoreline. So the first thing we did was we put in these falls, these reef falls they're called. And these reef falls, if you notice, they have a lot of holes in them. And those holes allow for water to pass through. So they're not going to a wave won't just break and everything just goes backwards, or the energy goes to the sides. In this case, a lot of the wave energy breaks, but a lot of the water still passes through and the sediment still passes through. Then on the other side, we planted salt marsh. So the goal was not to dissipate all the wave energy. This is important. We're not trying to reduce all the wave energy. We're trying to reduce wave energy during storm conditions. So normal waves just move through balls because they're sort of hollow. And big storm waves will reduce during storm conditions. And so when we have the storms, then we get fine grained sediment to settle landward of the reef. So we can then increase the amount of sediment available for the salt marsh grass to also then increase over time. And the goal is not that the reef balls dissipate wave energy. The goal is that the marsh itself that we rebuild will be the one that reduces the wave energy and protects the upland area. So why do we want to do this? Back in 2014, our colleague Iris Muller did a nice study where she really clearly showed that wave attenuation will happen on coastal salt marshes under storm conditions. What she did, she took, and her colleagues took 40 meters of salt marsh, like they literally cut out a 40-meter long chunk of salt marsh, and they put it into a flume. Do you know what a flume is? A flume is like a very long pool where you can then create waves in this pool, and it propagates down the pool. And what they did was they put little pressure sensors on this marsh that they cut out, and they showed how much the waves dissipated as they hit the marsh. Really cool. I mean, they did cut 40 meters of healthy salt marsh to do this, but once in a while, you can't save every tree. But what they showed was that there was a very strong wave attenuation during storm conditions, which is what we're looking for. So how do we learn about it? Well, the first thing we did, so we built this reef ball, we planted the salt marsh grass on the landward side of the reef balls, and then we put in pressure sensors to measure the waves both seaward and landward of this reef condition or this reef area. And we measured it during calm conditions and we measured it during storm conditions. The second thing we did was we tried to understand how much sediment was moving on both sides of this reef ball setup. And we used both high tech, so high technology, these are optical backscatter sensors that shoot out lasers, and with the scattering of the laser beam, they can measure the amount of sediment in the water. And we use a very low tech system, which I love. We call this a single stage siphon sampler. Basically, you get, and this is something, once again, low tech stuff, I love it. It's really easy and it's really nice to keep. You get, you take 9 bottles, and in each bottle, you put a stopper on the top. So there's some sort of lid. I find the stopper to be good, and the stopper has 2 holes in it. And one hole is attached to a tube that's attached to a pole that goes up into the air somewhere. And the other is attached to a tube that then goes up and back down on the pole. And the opening is where it's going to take the sample from. And the curve height is where it, or when it's going to take the sample. So once the tide goes above the curve height, water will be pulled in from the opening into the sampler. So you can get ground truth samples or real suspended sediment concentration samples by both tide height and water level that you're interested in pulling it in. So what we did is we have then this array of 9 bottles. So we have basically a bottle that's going to measure then, let's say at 20 centimeters tidal elevation, but it's going to pull water from 5 centimeters, 10 centimeters, and 15 centimeters. That's one row of bottles, 3 bottles. Then we have another one that the tube, the curve will be at 50 centimeters tidal elevation, and it's pulling from 5, let's say 15 and 40. And then we have a third row of bottles, and maybe the curve is at 1 meter elevation, and then it's pulling at 5, 50, 80 or something. And then we can really get a nice integration of our suspended sediment concentration to ground truth our OBS sensors, but also really nice way of doing things. One key is you have to build some sort of cage, otherwise they just float away. So, but this is something that you can easily do in your marsh situation. So like, for example, back behind the barrier post, if we want to see how much suspended sediment our water column. So once again, here's our reef ball setup that we put in there. These are pressure sensor pairs. So both landward and seaward of the reef balls. Our suspended sediment siphon samplers were on both the landward and seaward side. And then we had some auto samplers, which we get into. So this is pressure sensor data from both the seaward and landward pressure sensors. And basically, well, this is just zooming into, let's say, the area with the highest waves. And basically what we found was that during calm conditions, there's no difference in the waves in front or behind the reef ball set, which is what we want. We don't want any change during calm conditions. There's a little bit of change in it. But During storm conditions, we see 10 to 20% reduction in the wave height, which is a good amount. Because suspended sediment concentration is exponentially linked to significant wave height. So with just a few centimeters increase in wave height, we get a lot of resuspension once we pass a certain threshold. So the larger the waves, the more energy is in the waves. The more energy that's in the waves, the more shear stress that's in the waves. The more shear stress that's in the waves, the more we erode. So just a small reduction in wave height during storm conditions can really reduce our erosion potential. And that's one of the goals of the reef balls. This is basically showing that. So once again, the wave height is directly proportional to what we call orbital velocity, or Umax. And Umax, or orbital velocity, is proportional to sediment resuspension because of the empirical drag coefficient. So the larger the wave, the higher the orbital velocity. The higher the orbital velocity, the higher the shear stress. The more shear stress we have, the more we suspend sediment. So by putting in these reef balls and reducing the wave height, we're able to also reduce the erosion potential behind the reef balls. So this is kind of our setup, what it looks like out there. Here you can see the reef balls. This is basically right after we put it in. This is our siphon sampler system. You can see the tops that are open to the air here. So we have about a 2 meter tidal range. So at high tide, we these are still able to pull in air, and the looping of the siphons down below. And this here, this is our auto sampler system. Sylvina, I think you were there when we put that in.
I was talking about this, but it was covered by snow.
Yeah. There was, I think about 30 centimeters of snow when you were out there. But this is an auto sampler system. So this guy inside has 24 sample bottles, and it's also then pulling water from a different area. And you can tell it when you want it to sample by text message. And then you can collect those samples once again to ground truth your whole data. So we have a lot of different things going on here. Truly understand not just the wave movement, but also the suspended sediment concentration. Yeah, and it seemed to work. So they put in another row of reef balls. They got a little bit more excited. And we really started to protect this shoreline. And here's just some images of it. And so this is the reef ball. This is all marsh here. It's also a little further offshore. And this is, you can see the erosion, the dune behind it. Here's some erosion going on here. And over time, we can start to see that we're getting a little bit of growth behind the reef balls. Getting some sediment to deposit, to accrete, and we get growth behind the reef balls. It's a nice photo of reef balls. But the point is actually you're supposed to see that there's some barnacles starting to grow on the reef balls. So there's some biology that's starting to attach to it. And our goal at the end is that this is basically covered in barnacles and oysters. Over time, here's see the barnacles maybe a little bit there. And
It's not there, right?
sorry?
It's not there.
Yeah, the snow.
Está muy calentito, -12 grados.
All low tide. So at high tide, it's basically covered here. So you can kind of see the high tide line back up here. But yeah, so at high tide, the balls are more or less covered again. And so we're starting to get our grass to grow, and you can see that right around the grass, which is also helping, there's a bit more fine grained sediment than the rocks that are right by the reef balls. And then over time, the grass starts to grow more. And about 5 years later, we have a lawn. So we were really able to restore the salt marsh here. And this was about 5 years. And you can see that within those 5 years, you get healthy marsh grass growing behind here. And then what we have really is, like the marsh is now the main protection of the coastline and no longer the reef walls themselves. And we're not the only people to do this. So this is an example from Alabama where they put them in here. They have 4 lines of coast and then they get some salt marsh behind it. And if you Google reef walls, you can see a lot of information about this. So these are nice because they're not just a breakwater. The holes allow for the biology to grow. They're allowing water to pass through, which allows the fine grained sediment to come out.
John, the storms there, they're not really strong because they just make deep waves and trees.
So this is
Maybe not,
where we.
they don't think either.
Yeah, so where we did it was in Long Island Sound. Long Island Sound is a fairly large water body, but at its widest, it's only something like 70 kilometers wide. So we're not getting 5 meter waves or 4, maybe you get 1.5 meters, 2 meter waves in real storm situations, but it's never gonna be much more than that. The fetch isn't big enough. So to put this on an open ocean coastline might be different. So I'm not saying it's necessarily for this coast here, but maybe if I don't really know the full coastline shape of Argentina, but maybe in some of those places where it goes in and out, that's where you might be able to put something like this, or along the Plata, Rio de la Plata coastline. In there. So the second nature-based solution project that I wanted to talk to you about is a very present project for me. This is happening right now. We're trying to restore marshes in the Venice Lagoon in Italy. Just checking my time.
We start like 2 minutes later, so.
So I always like to show Venice. Venice is a beautiful city. And Venice is an interesting place for multiple reasons. I'm sure you know about Venice. I don't need to go into too much of the history of Venice, but Venice, just briefly, was built essentially on a salt marsh. So Venice, the city of Venice is in the middle of the Venice Lagoon. The city itself is only about 10 square kilometers. But the lagoon is 550 square kilometers, so it's a very large lagoon, and a lot of it was salt marsh over the years. And so we have these buildings built on salt marsh. They're clearly no longer available for protective purposes, but all around the city there are still salt marshes, and those salt marshes help to reduce flood energy in Venice. And as everybody's heard, Venice floods a lot. So Venice is a flooding issue. But one of the problems is over the last 30 to 40 years, Venice has lost something like 60% of its salt marshes. And it's lost those salt marshes for a few different reasons. One, sea level is rising faster than the salt marshes can keep up. That's a big issue in Venice. Venice has both global sea level rise issues and local sea level rise issues because they pumped all the groundwater out for many years. So the city has sunk to relative sea level by about 30-35 centimeters in the last 100 years. So that's faster than the salt marshes could accrete, and therefore we lost a lot of salt marshes. Other salt marshes were lost due to construction issues, et cetera, but over the years, we've lost now 60% of salt marshes, and we're trying to restore this. We're trying to restore these salt marshes. And what they're doing, so not us, but what the city has done is they've been dredging a lot in the canals of Venice. They dredge so the ships can go into the city of Venice, and they dredge because of this Mosaic project, which was built to protect the city from big floods. And they put those dredge spoils in areas to restore marshes. So they pumped them into an area, they cordoned it off, and they said, this is gonna be a new salt line. But they didn't really think about it. They didn't really think about what's gonna happen when they did it. So we have a group of people, well, actually there's a few groups, but our group is looking at a couple of specific marshes where they were infilled in the last decade to try to understand what's happening. So one of those marshes is this one here. It's known as Piove Gabora, which is down here near the southern lagoon. This is where all the ships come in. And Piove Gabora is a marsh that really is more like just an infill. So you can see here, the marsh was supposed to be this big, which is quite large. And they put like they put wooden pilings around the edge. So they pumped up the sediment, put wooden pilings around the edge and said, be a marsh. And that's all they did. And the interesting thing is some of the area actually started to develop a bit of marsh, but a lot of it didn't. And we're trying to understand how we can improve this so we get more marsh area. So the first thing that this group is doing, that I'm now a part of, is actually opening those fences that they put in to the marsh. So those fences were there to supposedly hold the sediment back. But the problem is that they were also preventing the marsh from developing. They were preventing the marsh from getting new sediment onto it. So they started to open the marsh, and they did it in two ways. One way, they actually just removed part of the fence. And the second way, they removed the geotextile that was also preventing water movement to try to understand what's happening here. And so this is just some photos of that fence line, so you can see it a bit and how they try to remove it. And so now we have some drone surveys, February 2023. And this is when the fence was still there. And then they cut it. And you can see that this marsh creek is developing more. And marsh creeks are really important because the marsh creeks not only allow for the water to come up onto the marsh and provide new sediment to the marsh, they're also important for the ecology of the marsh, allows the fish to come into the marsh at high tides. These marshes are great nurseries for fish. The other thing that they're really important for is draining the marsh. So the marsh needs to drain over time. Tide comes up, and then the water comes onto the marsh, but the water has to come off the marsh. And kind of the faster it comes off the marsh, the better it is for the properties of the sediment to settle, as well as the natural nutrient cycling of the marsh. So the marsh creeks are really important. So we have marsh here. Once again, this is cut, in February 2023. They remove it, and within a half a year, we get a bit more development of Marsh Creek. In this area, section EE, this is one of those areas where they didn't actually remove the whole fence, but they just removed the geotextile protections. We have an image from February 2023. And then September 2023, you see this beautiful development of a marsh creek that's happening here. And now going further in time, once again, February 2023, we have the removal. September 23, we get development of a marsh creek. July 23 is the second one, September 23. And now finally, February 24. Not only do we have the development of the marsh creek, we're starting to see some vegetation occurring around the marsh. So we're trying, so once again, Leo, to go back to your question, the goal is with all of these situations is to redevelop a natural system. So It's good if the accretion is happening faster than the natural system in the beginning, but eventually we want to get back to a natural system. And one of the most important keys to a natural system in marshes is the marsh creek development. So this is what it looks like if you're standing on the ground there. You can see this nice marsh creek is being developed. We get some primary growth along the marsh creek. And eventually, we're hoping that this establishes itself and we get some salt marsh grass growing here.
Both methodologies were successful in this case.
And both were successful, but it seems like, I think they had decided that actually just removing the geotextiles is better than having open a whole hole. And first of all, it's a little easier, and secondly, you still have that kind of protection associated with it. So they have their marsh area here. This is kind of, if you look back to the original image, sorry, I'm gonna go back a few slides. One more. If you look back at the original image, this is basically desert. There's nothing there. And now, sorry about this, gonna go forward a bit. And this is now about 2 years later, and you can see there's some growth happening on the marsh. So instead of having just maybe a hectare of marsh, you can increase it to about 5 hectares. But they're doing a lot of things, or we're doing a lot of things to monitor this marsh. First, we have set up time-lapse cameras on the marsh, so we can see how the marsh floods and then ebbs over time. We can see where that water spreads to. We have piezometers in many different locations on the marsh. We'll talk about that in a minute. And we've also collected or put in kaolin, which is like a marker. It's a type of material that you can then put on your sediment to mark the sediment to see how much it's accreting over time. So then you dig your hole and you find your kaolin there. You say, okay, we put that in there in January 2023, now it's January 2025, it's accreted 2 centimeters, it's a centimeter. We have some markers for that. We don't have that here, but in our next location, we're gonna put in sediment traps to actually see how much is being collected. And there's been sampling for NDVI, so the vegetation index by drone to see how much vegetation is increasing. We also do this ground truthing, ground cover and ground species cover. You put out one of those quadrats, so 50 centimeter by 50 centimeter quadrat, and you see how much vegetation's in there. So we've got a lot of different things going on. The biologists in the group are doing invertebrates and birds. Yep.
Yes.
Very high resolution VMs as well. I'll show you an image for that. So we can also see how the accretion is occurring over time by DEM. The problem is with salt marshes, especially in short time periods, the accretion we're talking about is millimeters per year. So even in high resolution, that's tough to see. But we're hoping that it's increasing over time. So speaking of DEMs, so here's a digital elevation model of the area. Reds are the higher elevations, blues are the lower elevations, and you can see we're talking about a total of 1 meter here difference between, let's say, the channel and the high marsh. And you can see here the more developed marsh is also more high marsh. That means it's flooded less often. It's then able to protect the city of Venice better by reducing flood energy. We still have a lot of low marsh here, but what we can see is that marsh creeks are developing. So this is that one that I showed you earlier that had essentially nothing and then developed over time. This is the EE survey. And we can start to really see these marsh creeks developing. So speaking of marsh creeks, what we call channel development, so EE is this one down here. So if we look at EE, it was cut, it was cut in February. And already by July, we have a length of 60 meters. I mean, that opening was made in February. By July, we have a total length of 60 meters. By September, it's now 75 meters. By the following, so 1 year in, it's 90 meters. And then at that point, it seems to have stabilized a bit at 90 meters length. And here's the volume of the total marsh creek. So you can see that the volume's increased to about 8 to 10 cubic meters of marsh creek. So this is allowing the marsh to drain better. This is another one that I just removed the images from, so we were here all day, but DD was also cut in February, and you can see it increases a lot in 1 year, then it so this is, once again, looking at the channel evolution. This is the DD one. So once again, this is we've just removed the geotextiles on DD. We haven't cut a hole in it. You can see July, there's already the formation of a creek. September, it's getting nice and big. February, it's now kind of reached its normal level. July, we get the vegetation growing around it. Look at the difference in vegetation between July 23 and July 24. So we really see that these marsh creeks are increasing our vegetation. And these are our profiles of the creeks. It's a little hard to see, but July, September, February, July the following year. So you can see it's increasing, the volume is increasing over time through this marsh creek. And the different sections, this is blue, the top one is close to the opening. The green curve is sort of far away, and the middle curve is this pink, it's really purple curve. But you can see that in all cases, it's really increasing with time. So just by doing simple measure, so the city pumped all the sediment, they spent millions of euros. I'm thinking like 30 million euro a year pumping the sediment. But they didn't do anything about it. They just pumped it, put the perimeter in, and left it, and nothing developed. But just by opening some areas, we start to increase the development. Simple change. This is the time-lapse cameras that were installed near the opening. You can see here, once again, the geotextile is removed in this area, so that's where the marsh creek is forming. And we look at how the inundation, the daily flood and ebb changes over time. So this is just some images that you see. We have two locations. We've got one near the EE and one near the AA. So one where we've actually removed some of the fence, and other where we just removed the geotextile, and we can see that change over time. And this is hard to read. This is just preliminary results, but it looks like the change here, you can see the change in green. The difference between the flooding originally, right when they opened it, and the flooding a year later, is we've got a bit more water moving onto the marsh because of this opening. This is really preliminary evidence, needs to be analyzed. The next thing goes into the groundwater, and I think this is where some people in the room get more excited. So we also have piezometers all over this marsh. And the piezometers were put in, I think in 2023, to try to understand how the water table underneath the marsh recovers during every tidal cycle. And these piezometers were dug, they're all about 5 meters deep. And they were put in near several channels, near this fence, try to understand how things are changing with time. This is what one looks like. And in each of the piezometers, there's your typical hobo pressure sensor measuring over time. And what we can see is in 2023, how the water level in the piezometers responds to the tides. And then this is in this is June in 2023, this is July 2023. How the water level responds to the tide. So these are our different piezometers. And basically, you know, when the tide goes up, the water level goes up in the marsh, the groundwater level. And then as it goes down, it falls basically with the fall of the tide. But you can see that it actually, at some point, especially in these like P3 and P4, this response level is really slow. So it responds fast when it's basically above the level of the marsh. And then once it gets to the marsh level, we get a bit of a delay, a lag time between the level of water below the marsh and the tide. So you can see we have this pretty strong lag time here. And then after the channel develops, we get a much faster response. So the channels are helping to drain. And this is once again, it's a bit preliminary, but the channels are helping to drain the marsh. Which
Sediments are exactly the same, I mean, they build.
so the same area, it's just that the channels formed. So the channel is now draining marsh. So at least in these P2 and P3 piezometers, which are located here near a marsh creek and here kind of near a marsh creek, we see a better draining of the marsh after the channel develops.
What about recharge? What do you see that in this? I mean, how is it?
I have
Is receiving any, I mean, it rains, but how much it rains in Venice?
meter here.
So it's pretty much, you might see something related to storms,
Yeah.
charge of fresh water or something.
Probably. I don't know if it's as important as the tide coming up because the tide's just completely inundated. But maybe in the high marsh, you would see that. So in the high marsh, you might get a bit of a fresh water sitting on top of the salt water, but I don't know if that's been looked at. I'll let you know. And finally, we can see our vegetation differences in February 24 to February 23. And the green, darker greens mean there's more vegetation in February 24 compared to February 23. And you can see this is where a lot of this is the EE location. We get a lot more green here in the marsh channels in 2024. So it's really helping to improve the vegetation on the marsh. And the vegetation is critical to the stability of the marsh. It's no longer an infill than a marsh once we have vegetation. Good. So this brings us to the next part of this story. And we're trying now to kind of also not only open these marsh creeks, but actively protect the marsh as well by putting in fascinae. So we put in fascinae on a different marsh nearby. It's another site that we have. And the fascinae, the original fascinae were pretty small, just about a line of 36 meters, one fascinae thick. And we're trying to see if the fascinae themselves help to reduce the wave energy that comes onto the marsh and help to capture sediment. So we put these fascinae out in 3 different locations on the marsh. And we have pressure sensors on both sides of the fascinae on the 3 different fascinae. And we also have suspended sediment concentration meters. This is the Argus sediment meter, and that has, what's interesting about the Argus sediment meter, it has OBS sensors, so that optical backscatter sensor that I talked about earlier, but it has in every centimeter for 144 centimeters. So you can integrate an entire water column. I think, did Mark bring them here? Mark found them. So, and then you have to do calibration experiments in the lab to see how they work. But basically, we put them also in front and behind the fascinae to see how sediment moves. Yeah, and this is our other marsh that we're doing this on. So this is what the Fishine actually looks like from the drone survey. And so we put our pressure sensors sort of seaward and landward of the Fishine. And we also, this FS is where the ASM sensors are, so the OBS sensors see how the marsh responds to waves. And so we put the pressure sensors out there, and basically, unfortunately, the time we did this research, back in September, there were very little wave action. So I don't have too much to say about this yet. What I can tell you is visually, the area behind the Fishine is incredibly calm. And seaward of the Fishine, you can see the little ripples on the water. So we're hoping the Fishine break the waves. The actual data is very limited. So there seems to be a reduction in the waves, landward of the Fishine compared to seaward, but this is 1 centimeter. So we're talking about very small waves. So I don't have real data to show you yet about that, but our goal is to put in a larger system of Fishine on this marsh in order to really help this marsh recover and grow. So you can see here, we have high marsh. In this high marsh area, there is some vegetation in there. There's actually a marsh creek that's developed, and there's some salt marsh grass. In the low marsh area, which is huge, there's nothing. It's not a low marsh, it's an infill. So what we want to do is we want to put in a large system of Fishine down here. We basically said we're not going to recover this area. This area is too low. It's just they didn't put in enough sediment. But we're going to put in a large system of Fishine in this area. So from this point to here is 150 meters. We're going to put 150 meters by 10 meters of Fishine in. And we're going to try to create a high marsh in this area that will then help capture sediment that comes from other areas, and we're hoping will grow back towards the high marsh and at least add another several hectares of marsh to the area that's developed properly. So 150 meters by 10 meters of Fishine, it'll be like a honeycomb. And we'll also put in openings. So we'll put in openings through the Fishine that are like marsh creeks. We'll see if that works. And then within the Fishine, we're going to use oyster shells to also hopefully encourage sediment accretion and also raise that elevation a bit. So if you look at the elevation map of the area, sorry, I don't have a scale, but the brown, this is higher elevation, and we want to put the Fishine in down here, and hopefully increase the elevation behind it. And it should look something like this, but a bit more, a larger space in between the honeycombs. So the honeycomb is not going to be, I think here's about 50 by 50 centimeters. It's going to be more like 1.50 meters by 1.50 meters. And it won't be so regular. We're going to make it a little bit more irregular, because irregular is probably more of a natural system. And inside of these, we're going to put in shells inside of this. This project, these Fishine, you would think they're cheap, but they're not actually that cheap. So this whole project is going to cost about 200,000 euro to put in this Fishine system and the shells. The shells are also expensive, even though they're just a waste problem. But we're hoping that they'll understand that this is actually a good way to do it and reduce that reduce that use of waste over time. And so we're trying to create a circular system. We're trying to create a system where the sticks, they come from the lagoon, they come from the area around the lagoon. The shells, they come from the lagoon. People have eaten the shellfish, and now the shells are going back onto the lagoon. What's crazy is how many shells we need for this project. We need something like 20 cubic meters of shells. That's a lot of shells. Because we're just going to fill it in only to a few centimeters to get that. And our goal is to see if over time we can now increase the size of the marsh. We're gonna do multiple individual experiments within a large experiment. So we're going to have, for example, different size marsh creek openings. We're gonna do areas with shells and without shells. We're going to seed some parts of this with salt marsh grass, and we're gonna not seed others. So there's like 6 different experiments going on within one experiment here. But this brings me back to the point of economy. So our goal is to show that using products created by the Venice Lagoon, we can help to actively increase salt marsh success, salt marsh stability, restoration of the area, at a cost that's then cheaper than just pumping more sediment. So I said this costs about 200,000. But if it helps to restore 3 hectares of marsh, we know that the pumping of sediment, 3 hectares of marsh, is about $1 million. So then we can show that it's actually better to pump less sediment and then put these there to actively restore the marsh than to pump more sediment. Okay. That's the first thing. The second thing is, we're also trying to talk about ecosystem services. So we have a group of economists associated with this project that are trying to understand, trying to value ecosystem services. And say, for each hectare of marsh, you get X amount of carbon sequestration. That is worth €10 per, I don't know, kilogram of carbon dioxide that you're sequestering. And you get 100 kilograms per day. And then you can get a value of how much these marshes are worth. Because this environmental resource economics is really the key to getting people to support these projects. The more you can show that the project actually brings in money, the more likelihood you'll get the politicians to be behind these projects. It's a bit complicated. It's not a one-to-one system because there's always real money versus, imaginary money from the ecosystem service, but it's still better to be able to show, okay, it's cheaper to do this than just pump sediment. And then we also get these services. So that's kind of the goal of this project. And this huge construction is happening in April of this year. So I basically fly back to Kiel and then fly down to Venice to set up this project. So we'll see, we just ordered all of these machine. And the logistics of it are really intense. And it's one more thing that I wanted to bring up about this. We also have one student who's trying to understand what is the, say, the footprint of the construction itself. So when we go out there, we're gonna have 10 people walking for 2 weeks, all day, back and forth on this marsh. That's damaging the marsh. So we can't just say, let's put this in, great, we'll measure it, we'll monitor it, we'll put some pressure sensors, et cetera, and it shows that the marsh is growing. But if we damaged a significant portion of that marsh to build this, is it worth it? So you also have to think about that. When you have, it's like a bunch of cows going back and forth over an area, eventually the sediment gets softer, that's gonna lead to erosion too. And so we have a student who's looking at that, trying to measure compaction, erosion rates in the area where we're transporting this. So it's really trying to look at it on like a holistic, comprehensive project from every angle to see if this is worthwhile to do. So it's truly a natural experiment. Which brings me to a question for you.
The area is too low when you show first. There is no way, they need to pump more sediment, or there is no way to cover this area.
No, we would have to pump more sediment. So we're talking that the whole area is about 3 hectares. that's too low, that we think we can save, and it's all about 20 to 30 centimeters too low. So we're talking about pumping many cubic meters of sediment on there, and the thing is, if you just pump it on there, which they did in the past, maybe it just goes away again. Because you can't just, what we're learning is you can't just pump the sediment up, you have to do things to improve the area, so put in the marsh crates or plant salt marsh shoots, stuff like that. So we're seeing if we can actively increase sediment increase with one of these type of setups here. So I have one or two more points about this, but first I have a question for you. What do you think, what type of nature-based solutions do you think you could implement here in Argentina? Either in the Rio de la Plata or on the coast? Anything?
I was already. We propose to the authorities on the shoreline protection plan, but they are against these projects because they don't like, for example, the intertidal vegetation, because people went there for tourism. They like the beach with sun, but they don't like the beach with the marsh. In that, it's one of the main problems. It's proposing this kind of green solutions.
So,
local authorities and people use the coast.
so for the audience that's online, I think just to briefly summarize the point that there is the attempt to put in a living shoreline about 100 kilometers from here in the estuary. But one of the big issues is that the people themselves would prefer having a beach than a salt marsh in the area, that it's just nicer to hang out on the beach than it is to hang out in a salt marsh. And I think that is a major issue. And that's also where we did the reef ball experiment in Connecticut. I think maybe one of the photos, you could see that like nearby there was a beach and there were houses along that beach. And we had the same issue there, that the people there didn't want those reef balls anywhere near them because until the marsh is there, the reef balls themselves are kind of ugly. And aesthetics is a big issue. And the second thing was, yeah, we don't want a marsh in front of our house. We want beach. And so we couldn't completely get around the whole thing. What we were able to get around was, okay, we're not going to do this in front of your house. We're going to do it on the end of the area where there were no houses. And within 10 years, you're not going to see these balls anymore. And then but you'll also have, reduced flooding in the future, et cetera, et cetera. And they were okay with that, but they would not have been okay with putting the marsh on their beach. So I understand what you're saying. And I think that's something that, once again, it's this compromise issue, that maybe there could be a compromise. Okay, we're not going to, put this everywhere along the coast, but we're going to choose 500 meters to try to restore as a test project, to see if we can then reduce the energy, and you can show that behind those 500 meters, everything's healthier than where it doesn't exist. And then maybe people will get behind it over time. It's not easy. Don't have I understand your problem here.
Problem happening here in the coast. They build a seawall and they destroy all the natural vegetation. They solve the problem, but there's a lot of money to build a seawall. That's a problem too.
Yeah.
They are far more expensive.
The planting some seagrass or some salt marsh. Yeah, it's And the other thing is, this is another issue, is the perception of people. When they see a seawall, they say, the government is doing something. They built a seawall. It's very easy to understand the seawall. The waves are no longer breaking on my house, now they're breaking on the seawall. Whereas if you build a marsh or you do something natural, they don't, people struggle to understand that that's also something that is a government project or is a good government project. So that's another perception issue that is difficult to get over. Yeah. Yeah, I mean, it almost takes a centralized decision to make these things go forward, and I know that's hard. So, for example, in the US, basically, you're not allowed to do any more hard protection. There are certain instances where they'll allow it, but mostly for the last 10 years, only soft protection is allowed. So it has to almost come from the governmental level, like we're not gonna do hard protection anymore.
Yeah, but I still, I told you in Las Colinas, they show, I mean, they asked for a study to a professor of the University of Mar del Plata, Miami. And he recommended some like a database solutions like soft protection. And after this study, after this recommendation, the province got money from the national government, and they start building the things.
Yeah.
They ask for the recommendation to the university, to the people who knows, who is like an expert in erosion, and then they do exactly the opposite things.
The problem is that engineers still, they are still recommending structure.
Yeah, that's true, and that's history.
Yeah, what John mentioned, I was talking to the person who lives behind the last one of these structures, and she said, yeah, the house is a little bit more protected, but we are already seeing erosion just next door, let's say, because it's the last one of the structure. So exactly what is happening. They're protecting a little bit, one part, but they're already destroying the next part of the beach.
And what you're gonna end up with is then these built in and armor the whole coastline, and then they're not gonna armor in front of the natural area. So the dune area is relatively natural, and that's what's gonna, so you're gonna lose your natural areas.
That's what's happened. The last one, and then it was the natural, and the natural was starting to be eroded.
According to the natural issue here of our coast, Buenos Aires province, we have different type of coast. They are erosional and they are accumulation, so they need different solutions.
Absolutely. Absolutely, there's not one.
Exactly. Observe or preserve the dunes or create dunes, and another side you need to show the erosion from the sea.
Yeah.
So they are different methodologies to apply to mitigate that.
Yeah, absolutely, and you know, in some cases, maybe you could even, let's say, try to move some of the area where you have the accretion down to the erosive area, but then you have to somehow stabilize that, so it's not just being lost again.
Yeah, the coast is a dynamic equilibrium,
Yeah.
and you need to play with that.
Yeah. The problem with the dynamic equilibrium is sea levels rising, right? So that's ruining the dynamic equilibrium, and that's gonna lead to more erosion. So theoretically, in the absence of sea level rise, there is kind of this dynamic equilibrium. You have winter storms where your beaches erode, you have summers where they build back again. But once you have the sea level rise, you get that issues like in Marda. Yeah, so it's difficult, but there's a lot of things, yes.
In areas with cliffs, there is some frutas and there have like big small cliffs. And there's a beach part, and then there is this large 2 kilometers rock platform. So very like obvious big tides. You have the tide differences like a lot, and the people are. and then the cliff starts falling down, it is eroding. What can you do there? Because you can't do submersions, there is no place, not marshes, you can do barriers, but
But additionally to that, that is the Patagonian coast. The tide is really, really gigantic.
It's 4 meters, maybe.
Yeah, maybe running away from the coast to then come to a short time. It's difficult.
Is it,
High energy.
is it just tides or is it also waves that are initiating? So in other words, is it just the current from the tide going in and out? Or is it also?
there's the waves that come.
So the waves are also powerful. Yeah.
This is the ratio and the low tide, suddenly camp, waves against the cliff.
They are.
Yes.
So there's two ways to think about this. Is this, we have similar coastlines in Germany, and this was a discussion recently. Should we protect the cliffs? Because cliff erosion provides sediment for other coastal areas. So it's not necessary, like, I mean, if you have a house there, it's always a problem, right? Because then it's very hard to say, let your house fall into the sea.
They are related areas, you have like, there's houses and the cliffs.
Yeah, so if
You are thinking like a creature, but you want to think that a human being,
yeah,
they are living that.
I mean. Cliffs are difficult to deal with, as you said, a little bit harder. I mean, theoretically, naturally, letting the cliffs erode is a natural process. And unfortunately, there are some proponents that say the best way to deal with this is what's called retreat, coastal retreat. So actually, the people have to move away the coast. Easier said than done. Most people are not going to want to retreat, leave their houses. There is.
So in some places the houses are already falling apart. In that case, you don't have.
You don't have to worry about it. So there is an idea, and I don't know how well developed this idea is, I've been also thinking about this, but there's an unbelievable amount of energy in waves. I think there's an unbelievable amount of energy in waves. Theoretically, you might be able to have a double positive if you can harness the energy from the waves and reduce the wave energy at the same time. So you might be able to put in a system of wave energy turbines. They're like paddles out in the ocean. And when the waves come in, they move the paddles. And the paddles then move a generator and generate electricity. And at the same time, they're reducing the energy of the waves because the energy of the waves is now going into the electricity. So you have this double positive of building or of producing electricity for your people, your country, and reducing the wave energy to protect the coast. But this is sort of like in the infancy of the technology. But there are a group of people in Ireland at the Marine Renewable Energy Institute that are starting to think about this. We do want to capture energy from waves, that's not a new idea, but like this kind of dual purposing. Then we're talking decades before that comes into play. But it's an interesting idea that you could both protect your coast and produce energy from the waves in time. In the meantime, it's hard, and you could. I don't know the exact area, I don't know what the geology is like there, or if there's any possibility of trying to plant anything in front of that, or if it's really just rock.
I am not
It's rock.
from geology, but it's like from sand, compacted sand that I and so it's like a soft, it's not rock, sandstone.
Mm-hmm. But it's still stone, so you can't really plant it.
You have like these cliffs and the dune areas that don't have this. It was
just a question.
Yeah, it's a complicated question. I mean, you know, as I said, you're not a component of hard protections, but in an area like that, if you have to protect the houses, you might put in tetrapods or something like that, but that's hard protection. So somewhere else, you're gonna have a problem. Question is where. Any other ideas for nature-based solutions? Leandro, do you have an idea for how to change your cities? I don't know if you want to talk about that.
No, maybe.
You're not talking about protection, just coastal protection, just in general.
Yeah, nature-based.
It's one city or.
No, I don't think so, maybe. The solutions are for maybe, the solutions are not the same for different coastal settings. In Myanmar, the only solution was the thin fence, you see, in Myanmar, do you remember it?
Yeah, was
And
beneficial.
I think it works.
Yeah.
Works.
Yeah, but he's also asking about nature-based solution for anything, like he wants you to mention the.
Sponge city.
The sponge city. El modelo Jaime de lluvia.
So you're talking about rain gardens. Yes, and you know, there is a very situation that the first one with the city. So we are applying like a rain gardens in the you know, it's a water for about 100 a day. I don't know how to say hectares.
Hectares, yeah.
And we apply a lot of rain gardens in other buildings and new buildings. I think it works. So we see the level rise, maybe it works. And this is the structural items for the recharge, not for the issue.
So the concept of sponge cities is another idea behind, or another nature-based solution idea. It's that you reduce the impervious surface that's everywhere and allow the city to soak up precipitation. And obviously it has the benefit of increasing the recharge of your aquifer, but it might also have other benefits, such as if your aquifer recharges more, you get more groundwater discharging out, which then, you know, prevents saltwater intrusion. So you get that benefit. But the other benefit you might have is a reduction in the severity of storm damage, right? Because instead of having, like what happened in Bahia Blanca, your streets just fill up with water, and it becomes a disaster situation. Maybe a lot of that before, I mean, with that amount of precipitation, it's difficult, but it's still better. The more that can recharge, the lower your damage will be. So reducing impervious surface or increasing permeable surfaces have multiple benefits.
Yeah, but you also saw on the coast, I mean, you have many, even in this compacted sand, you have more of most of the areas with the streets are made of sand, they are not paved. But as you said, people want, for instance, to do the pavement, because of course it's easier to drive in a way with the street with the pavement, not with the sand. But usually people think that this is part of the, how do you say? The progress, exactly. If you live in the sand, or you are not living in like downtown, so you are in the suburbs, so it's no progress. And they don't understand that for the water cycle, this is really important. So this is part of the education. I mean, just the population and the governments, it's not just the authorities, not just the people. So we are trying to convince them about that, but it's difficult to.
Another problem I saw when the last time I went to Clases coast is some mining.
Mining, yes.
Beneath the vehicles and
Yes,
The guys with
the
the horses.
horses, yes, the one with the horses and the shovel, the city.
I don't know how that's.
And not only because they go with the machines and.
The same municipality do that, maybe some, for instance, to visit the roads, they go to the beach with the big machines, they shovel the sand and they restore the.
Yeah.
We have a people say you think.
Well, I believe that, and I know that these solutions aren't simple solutions, but sometimes it's just a little step at a time, you know, so, for example, our first salt marsh that we rebuilt with the reef balls was only 60 meters of frontage. It wasn't a huge area. It showed the people the potential, and so sometimes you can start small, it helps show people what kind of improvements you can make, so don't give up. I know it's difficult, but don't give up.
Now, it's important that scientists like you work in pilot project in order to try to find a solution to different cases. The thing is that this, you put the sites, the authorities with a positive result, and they apply that solution. When scientists have to do anything in any way that create a experiment, but the thing is to put the results on the government to say, okay, this is solution to the problem. Because there is there is a lack of communication between the scientists, the investigators, and the government of the people who decide.
That's why we have a president in control.
But really, but it's not a problem of politicians and the government. It's a problem of scientists. They finish the show, present the show, and finish. We should have a kind of commission that the result of the experiment go directly to the government to say, okay, man, this is the solution to that. It's different. You are dealing with that for many years ago, you also deal with it's different.
It's two parts, you know, maybe scientists, the scientists think that I will tell you the solution, and I will go home. Let's see, but for me, it takes for about 10 years, 18 years, again,
Yeah.
and one day, it will be the next thing. I feel the mayor saying in Kiel, the word aquifer.
After 15 years.
Yeah. It was so critical.
Yeah.
Yes, because finally the politicians are talking about it.
Yeah, absolutely.
Yeah, but I think it needs the two parts. And they
So the only advice that I would give you, because I don't know if you know this, but I also own a business, so I've got a bit of a business mind. Money talks, right? So it's really important to show that these things that you're doing will actually save money in the long run. And you have to do it very clearly. It can't be abstract, it has to be as clear as possible. If you do it this way, you'll have enough water, you can easily pump, you don't have to build a pipe to bring in water from wherever to the coast, which is gonna cost X billions or whatever, and now we can only do this little changes and that costs millions.
But actually, they're still talking about bringing water from Tandil,
Yeah.
which is 400 kilometers from the coast, because it's just,
Yeah.
yes, it's not, it's high, because no, you have to work here, you need to, whatever to manage the resource. No, let's bring it from some other place.
The other place we finished, talk with the new mayor of and talk about the values.
Is he open to any project or not?
But
One, is he open to the
Yeah.
project? Okay, now, depends on the person or the people that is in charge. In the civil work or the public work, because you can talk to a person and say, okay, really nice, sure, she had a here. And then you close the door and they say, okay, let's continue with the problem. Let's get more modes.
I think it's the same to say that you are doing is wrong, okay? I think find a way to send a clear message.
Yeah, and a positive message.
A positive message.
A positive message.
And then
Good job, but you could do it better.
Yeah, in my case, that I work more closely with the cooperativas that they actually manage the water supply, but still, I mean, it depends on the people inside the cooperativa. You met Oscar, he's just straightforward with the water, but he tries to convince the rest of the board behind him, because he's Oscar coming again with the water problem. Oh, it's always like that, and he in presentations, he explained the problem, says, okay, the university is working with this, with that, we need to help with this, with that, and then we are moving forward. It's really hard.
It's not easy to translate in terms of money.
Yeah.
You have to work with economists.
Yeah.
If you go with me, Harry, let's speak to people. Because I used to be at times in charge, not but helping the municipality of Villa in the beach situation they had. They used to have a road in the coast, they named Costanera. That was a kind of park inside to the beach, only that. But also most of the balnearios,
Beaches.
the restaurants and
Oh, yeah.
other places on the beach, down in beach, so it had as a seawall. So that I started to say, okay, we are in a wrong way. This is not the way to maintain our beach because we are losing it. And some politicians said to me, okay, tell me what is the solution that you can find. And I started to work with 2 or 3 architects in the civil works or public works in the municipality. And we try to figure out what is the thing that we can do, just destroying all the big buildings and try to create another kind of palisades, the woods in the beach, and destroying that street and create a kind of pasarela there. Was a nice tale to tell. And I presented to the parliament, the small parliament of the city, and say, oh, it's very cool, but we are now having a concession of about more than 20-25 years, so we cannot blow the contract and do that. Okay, that's okay. This is the project, I said. Was a book, probably fall into a box. But you know what? Happily, one of the architect was working in this, funny idea. In the time, reached the position of a public work director. And at the same time, most of the concessions were finishing and they want to renew it. And that means say, okay, let's renew the concession, but with this condition.
Yeah.
And now, most of the main beach of this agency is done in good, and also having that facility. Also working, in another country, but suddenly somebody told me, my brother said, you see, they are doing because I was always telling that 25 years later.
Well,
Kind of is lucky.
sometimes it takes time.
It's not really like this. Depends on the work.
It's a good success. It took a while. So I think we're well over time, so I just wanted to say thanks again for listening. This is the Puerto and Santa Ventin. And at sunset, I was there the other day, and it's really beautiful. You have beautiful marshes, beautiful marshes back there. So that's a good.
Not showing the kids.
That's the last one. This was sunset. Tomorrow I'll start the sunset.
Is it sunset?
Sunset and yeah, something like that. Very nice. Really beautiful area. Okay, thank you very much. Tomorrow we'll see what happens. One more class.
One more class.
So the new hotel. We switched hotels. And you know what? Yeah, you know what's crazy? It's only €10 more. So there's a roof. You actually come tomorrow night when you're done, it's important, but you bring us the stuff. Okay. There's everything. Yeah.
Sometimes it's.
Okay. It's really.
Yes, and have a nice